So today I'm going to do my lecture part of section 4.5, day 1. This worksheet is on Angel, so you should have downloaded it or printed it out. And I'm going to use these 6 new derivative rules in order to talk about how to take the derivative of the log of x and the log of a function of x, a to the x and a to a function of x, and a log base a of x and a log base a of a function of x. And we're going to just take these rules and apply them. I'm not going to prove where they came from or give a derivation for them. So if we look at our examples from the worksheet, number 1, if you had to take the derivative of the ln of 5x, then the first thing that you want to do is see if you can use any log properties to rewrite the ln of 5x. And since this is a product, we learned on Tuesday that you can write the log of a product as the sum of the 2 different logs, the log of 5 plus the log of x. So if it's rewritten like this, it's always easier to take the derivative of a sum. All you'd have to do is take the derivative of the ln of 5, and since that's just a constant, the derivative would be 0, plus the derivative of the ln of x, which we have right up here. The derivative of the ln of x is 1 over x. So we're going to have 0 plus 1 over x, or plain old 1 over x, for the derivative of the ln of 5x. And it doesn't matter if this is a 5 or a 6 or a 7, you're always going to get the same answer, because this part will always be a constant. The second problem is like it, except that it's the ln of the difference. So we can't rewrite it as 2 different logs. There's no property of for the difference, the log of a difference. So we have to look at this problem like this. We're trying to take the derivative of the log of a function of x. And in this case, the function of x is x squared minus 4. So that's my u. And we're going to use this rule that the ln of u is 1 over u times the derivative of u, which is 2x. And so rewriting that into one fraction, it would just be 2x over x squared minus 4. 1 over u du dx. Number 3 has the added complexity of a product, because you've got x squared, which is one function, we could call it f, and ln of x, which is another function, we call it g, and they're being multiplied together. So I have to use the product rule in order to take the derivative. So my derivative would be leave f alone, multiply it by the derivative of the ln of x, which again, we have the derivative of the ln of x right here. It's 1 over x. So when I multiply by the derivative of that, it's 1 over x. Plus, then I leave my second function alone, and I multiply by the derivative of the first function, which was 2x. So rewriting this, x squared times 1 over x is x. And we can think about this as the ln of x times 2x, or we could rewrite it as 2 ln of x, x. But what you want to notice is the common factor of x, because the best thing to do for your final answer is to factor that out so that you have it written as x times 1 plus 2 ln of x. And that's going to be helpful when we have to try and find critical values. So the derivative for number 3, remembering the product rule. And number 4 then is going to be the quotient rule. So we have a function with a function divided by another function. And the only way to take its derivative as it's written is with the quotient rule. The quotient rule says square the denominator, start with the denominator, times the derivative of the numerator, which we know the derivative of ln of x is 1 over x, so this is going to be negative 1 over x, minus the numerator times the derivative of the denominator, which is 2x. So simplified, this is going to multiply to negative x this time. Minus a negative can turn to plus. We can do the same thing by making it 2 ln of x, x, so that we can see that common factor of x up top. And x squared squared is x to the 4th. So again, we can pull out an x and be left with negative 1 plus 2 ln of x all over x to the 4th. And finally, divide out our x's. So the final derivative in a form that I can find critical values, it looks like this. So we've done all of our functions so far with this top row of definitions, taking the derivative of ln of x or taking the derivative of the ln of a function of x. And now we're going to look at the next set of problems which use the second row. So problem number 5 is the derivative of 1/4 raised to the x. Now we already know that if you take the derivative of e to the x, you get e to the x. That's something we've been working on before. That was on the quiz. But this is not e to the x, it's a to the x. It's a number other than e raised to the x. And so the rule for taking that derivative is when you take the derivative of some number other than e raised to the x, you have the ln of that number times a to the x. That's the rule. So what that looks like here is the ln of 1/4 times 1/4 to the x. It's almost as easy as e to the x. The only thing you have to remember is this extra coefficient. So we could think about this as the same problem, but we'd be saying that if we use that rule, we'd be saying that the derivative is the ln of e times e to the x, but the ln of e is just 1. So that's why we didn't have to worry about it when the base was e. It's just when the base is something other than e, we'll get this coefficient. So that's number 5. That's using a to the x. Number 6 is going to use this rule right here, the log base a of x. And number 6 looks like this. The derivative of the log base 5 of x. The rule says that it'll be 1 over the ln of the base, which in this case is 5. So 1 over the ln of 5 times 1 over x. That simple. You're just plugging in 5 where a is in your rule. And then finally, number 7 is 6 to the 5x. So the difference between number 5 and number 7 is the base is different, 1/4, 6. But the other thing, the more important difference is the exponent. In this case, the exponent is a function of x. Over there, the exponent was just x. And that means that when I try to take the derivative of number 7, I'm going to do it with the rule a to the u, a to a function of x instead of a to the x. So that rule is a little longer. It says it starts out with the ln of a, so in this case, that's the ln of 6, times a to the u, which is 6 to the 5x, times the derivative of the exponent, which is 5. So to write it more neatly, ln of 6 and 5, they're just numbers, constants, so we could put them together. And then put the a to the u on the end. So with 5, 6, and 7, you're really just looking at the derivative rule and plugging in. That's all you're doing. So those are problems on the test that you should definitely not miss, because I'm going to have this on the test, so you don't have to memorize any of that. Okay. Then 8 and 9. In order to take the derivative, oftentimes we have to look at the function in the easiest way that we could think about it. So if I wanted to take the derivative of this function the way it is, I would have to be using this rule, because it's the ln of a function of x. However, if I can use the properties of logs that I know to rewrite this, I might be able to do it a lot quicker. So if I use the properties of logs, and I thought about it as the 1/3 exponent instead of the cube root, then that 1/3 can come down in front. That's a property of logs that I have. So I could think about it as the third ln of x plus 1. This is now a constant multiple. And we know constant multiples always make our derivatives easier, because they just stay where they are, and you take the derivative of this. So I'm using the same rule, but my u is a lot simpler than it was in the beginning. Instead of a cube root, it's just x plus 1. So my derivative now, I leave my constant multiple where it is. I multiply by 1 over u, and I multiply by the derivative of u, which is just 1, because the derivative of x plus 1 is 1. So my final answer is 1 over 3 times the quantity x plus 1. And you would get the exact same thing if you use this as your u, but then you'd have to take its derivative, and that's not as easy as taking the derivative of x plus 1. So you want to use your properties of logs before you take the derivative. Same thing with number 9. If my function is the ln of x squared times the square root of x squared plus 1, you might start to think, oh no, I'm going to have a product in here and I need the product rule. But the good news is that we have a property of logs that says this doesn't have to be a product. I could rewrite it as the ln of x squared plus the ln of x squared plus 1 under a radical, which I also could think about it as power on x squared plus 1. So I'm changing the log of a product into a sum, which is always good because taking the derivative of the sum is a lot easier. But then the exponents in this problem, they could make things complicated, but we have a rule about exponents too. Those exponents can come down as constant multiples, which is going to make the derivative a lot easier because I don't have to worry about them being a part of my u when I take the derivative of the ln of u. It's coming down as just a constant multiple. So if I rewrite that in expanded form, which is what we learned how to do on Tuesday, then my derivative becomes so much easier because I just have a constant multiple times the derivative of ln of x, which I already know from my table is just 1 over x, plus my constant multiple of a half times the derivative of the ln of u, which is 1 over u du dx. So 1 over x squared plus 1 times 2x. And simplifying a little bit, I can put it as 2 over x plus my 1/2 and my 2 can divide each other out, x over x squared plus 1. There are people on this quiz who have tried to take this derivative without expanding it, and it's possible, but the algebra is way too long for this test. You'll never get through the test if you don't rewrite it. So that you want to make sure that you do that on the test. Anything you can rewrite and change into a sum or move exponents down will make it easier. And the final problem that I want you to see so that you can try your homework is the idea of doubling time. Oh no, I'm sorry, I'm on a different worksheet. It's the idea of estimating a log on your calculator. Because on Friday when I come back, you are gonna maybe have to come up with a value for something that looks like this when we're finding critical numbers. And if you notice on your calculator, you don't have a log base 2 button. So you can't just plug it into your calculator and get an answer. So the way that you estimate a log on your calculator is this, it's called a log conversion. And to find the answer to this, you just take the log of the argument 8 divided by the log of the base, which is 2. So if you do this division and come up with a value, which I don't know if I can do it because I don't know if I have my calculator, but the answer to this will be on your, is on the Angel website. The answers to this worksheet are all there, but I'll see if I can figure it out. Yeah, okay, so the log of 8 divided by the log of 2 is, oh, I should have known that, 3. You also can do the ln of 8 divided by the ln of 2. It doesn't matter what base you use, you'll still get the same answer of 3. But the reason I should have known that is the answer to this question is what power do I raise 2 to get 8? So it's 3. So if you have to calculate a log on your calculator that's other than base 10 or base e, this is the log conversion you have to use. And we'll be talking more about that on Friday, because on Friday we're going to take all of these rules for finding derivatives and we're going to take it to the next step to find the critical values. So we can find relative max, relative min, inflection points, all the things that we did on that last test we're going to do with logs on Friday. On Monday we're going to review for the test. The test will be on Tuesday. So please use all this information to try your homework. If you have questions, you can email me, you can call me, you can text me, or you can wait until Friday and ask in person. Thanks.